Okay, so we use an exponential equation for something that continues to multiply over and over and over again. So this base, which we call this base our multiplier, this multiplier can be a couple of things. Sometimes it's pretty blatant, like it'll say it doubles. So when we see words like doubles or triples or quadruples, or like you see today in class, you're going to see halves, that it halves. Today you're going to look at half-life. These words take us straight to the multiplier. Double would be 2. Triple would be 3. Quadruple would be 4. Today we're going to look at half-life. Anything that halves would be a half. So that's how it's growing or decreasing in terms of half-life. Now, we can have another situation with a multiplier where they give us a percent growth or a percent decay or decrease. Anything that's decreasing. So decay, eliminate, things that are getting smaller. So if they give us a percent to find that multiplier, we have to do 1 plus the percent written as a decimal when it's growing or increasing. So let's say increase here and decrease. So anything that means increase, growing, would be 1 plus the percent written as a decimal. Anything that means decrease would be 1 minus the percent written as a decimal. So we're going to kind of skip example 4 for a second because I changed that one. I told you to omit it yesterday. And we're going to look at 5. So this says a species of extremely rare deep water fish has a long lifespan and rarely has children. If there are a total of 821 of this type of fish, well, that beginning amount, that's our A in this formula. That represents our initial amount. So in this equation, this is our A. Yes, ma'am? Yes. Represents our number of time periods. So let's keep reading and see if we can find all these things for this specific problem. So this is our initial amount. So when I'm starting to model this, the amount of fish left after a given period of time. We start off with 821. That's our initial amount of fish. They're growing very slowly. Actually, that's not too slowly. Their growth rate is 2% each month. So they must not have many predators. So they're growing at a rate of 2% each month. So this defines what our unit of time is measured in. So for this one, our time is time in months. The word problem will tell you. Now, if it said the growth rate is 2% each year, then our time period would be number of years. But this one, because it says the growth rate is 2% each month, our time period is time in months. Then it says, how many will there be left in half of a year? Well, how many months are there in half of a year? So to answer half a year, that's right, we're going to use 6. Half a year is 6 months. So 6 is what we plug in. 821, 1.02 to the 6th. Okay, everybody get your calculators out. And I want you to use your graphing calculators, not your phones. Because you can't use your phone on the quiz, and I want to make sure you know how to use your graphing calculators.
With this one, since it's a living thing, do you still have to round up or round down?
Exactly. We're going to talk about that next. All right, so this is the answer I got on my calculator. All right, but because this is a discrete variable. This is a living thing. We can't have part of a fish that's living. We do have part of a fish, we call that bait. But we can't have part of a fish when it's living. Okay? So, this is not an acceptable answer. This is a discrete variable. So, because it's growing, we're going to round that down. When we have growth, we round down. So, the answer would be 924 fish. So, when we have growing, if it's growth, you would round down for a discrete variable. So that's a good way to think of it is anything that's living. Like if we're talking about people or animals. Okay, what will be the population in 10 years? 10 years. But my time has to be measured in months. So how many months are there in 10 years? 120. So this is what our equation looks like. All right, so we're going to get really big here. Now we're up to, this is what my calculator gives me, 8838.198. But we always round down when it's a growth problem. So this would be 8,838 fish. Okay, the last one is 100 years. So we would have to multiply that by 12 to find the number of months. And that gives us a big answer. Okay, so let's talk about what these big answers mean. I'm just going to write down everything I can see on my calculator, and then we'll talk about what it means. All right, that's a super big number. Because this e to the 13th at the end, what does that indicate? Scientific notation. So that means I would truly, if I wanted to write the number out, I would have to move the decimal place 13 places to the right, which I'm not going to do. So I'm going to write 1.716 times 10 to the 13th fish. And that's obviously approximate because I just dropped all those decimals. It would be approximate no matter what, because we can't see 13 decimal places on our calculator. Okay, questions about that? Okay, so back up to number 4. Suppose you began taking antibiotics after 1 week. Okay, so this ties back into number 3. See, number 3 is still on the board over there, okay? Which completely stopped bacteria growth and caused the bacteria to have a half-life of 12 hours. After taking the antibiotic for 3 days, how many bacteria remain? After 1 week, after 10 days. Okay, so this is half-life. So with half-life, we have to take the original amount times 1/2. This is half-life. So times 1/2. Now this is in hours. So we have to take the number of hours and divide by 12 because we get half every 12 hours. That answer was crazy big though, wasn't it? Yes, sir.
Is it saying half-life is 12 hours? Or
So that means if I started off with 100 bacteria, 12 hours later, only half of them would remain. So 12 hours later, I'd have 50. And then 12 hours after that, only half of the 50 would remain. So how many would I have? 25. Okay, so that's what a half-life means. But this is it takes 12 hours to have half of them remaining. So on this one, I started with that really huge number. Let's just do this number instead, because this is ginormous. Let's go with the 13 million. Let's say we started off with 13,382,588 bacteria. So let's say you figured out after a day you were sick, and you got the medicine after a day, not after a week. Yes, sir.
Is the problem different than on our sheet?
Yes.
Okay, sorry.
Yes. The problem is different than on your sheet.
So don't have this.
You can just follow along if you want to. Okay, so we want to know when half would be remaining. So 3 days. 3 days is our time. But our time is measured in hours. Every 12 hours. So how many hours are in 3 days?
72.
So we do 24 times 3 is 72. So in this case, we'd have 72 divided by 12. Okay, so what is 72 divided by 12? 6. So that means we take half 6 times. That's what that means. We take half 6 times. So we can punch it straight into our calculator though. We type in 13,382,588 times 1/2 raised to the 6th. So then we have approximately, we go from 13 million down to just 209,102.9. Okay, but half-life is decreasing, isn't it? So this is like a decay. With a growth, I round down. With a decay, I would round up. So this would round to 3. So when I have a decrease, or decay, you would round up. Okay, so the next one is after 1 week. So if we started out with a 13,382,588 bacteria, 1 week is how many hours?
168.
So we take 24 times 7 is 168. And 168 divided by 12 is 14. Okay, now some of you are thinking of it differently, which is absolutely fine. If it happens every 12 hours, how many times does it happen a day? Twice. What is 2 times 3? 6. Is that what we raised it to here? Same thing. What is 7 days times 2? What's 7 times 2? 14. So there are different ways you can think about it. All right, so here we do the 13,382,588 times 0.5 raised to the 14th. And we're going to round up Okay, y'all are really quiet. Do we get it? Okay, cool. So half-life is actually what you're going to talk about in class today. And then in your regular math class. And then what you're going to do is have some review questions too. And then tomorrow in your regular math class, you're going to have some more review. And then you're going to quiz Friday in your regular math class. Our quiz and support is tomorrow. Okay? So we're going to go ahead and start our review today. Let's talk about what we've learned since we got back. We did properties of exponents. Okay, so what does that mean? That means when we multiply like bases, what do we do with the exponents? Add them. And you do not have to write this. When we divide like bases, you can think of it as subtracting or canceling. So what would this be? I really don't mean to make them all be 6. Alright? When we raise a power to a power. Now I mean to. When you raise a power to a power, what do you do with the exponents? Multiply them. Okay? So, multiply like bases, you add the exponents. Divide like bases, you subtract, or you can think of it as canceling. Okay? Power to a power, you're going to multiply the exponents. Okay, so that's what we did the first 2 days. Oh, that stuff we did the first day on the graphing calculator, not on your quiz. No graphing calculator stuff on your quiz. The intersections on the graphing calculator? Yeah, that was last Wednesday.
I don't.
That will not be on there. Okay, so this is the first thing that will be on there. Okay, then we talked about negative exponents. Negative exponent, reciprocal. Negative exponent, reciprocal. And then we'd square, in this case. Okay, so we talked about negative exponents. Now, what happens if we have a negative exponent inside other stuff? Okay, so if we have a negative exponent inside a fraction, just those things raised to the negative exponent move. We don't flip everything. So the 4 and the A don't go anywhere. The C would move up, the B would move down.
So like if only B had negative 2 squared, like you would put it at the bottom?
Yep. Now, if everything moves out of the numerator, what do we have to put in its place?
1.
A 1. Good. Okay, then we did, given a radical, write it as a rational exponent. So this would be power over root. Power over root.
Going backwards was hard for me.
Then we went the other way. Yep, we did. Say we started with like this, and let's say we did negative 3/4. So the negative tells us to do 1 over. The power is 3, the root is 4.
Did you guys take like a Blackboard quiz today? I didn't
Did y'all do that today?
Yes.
Cool.
Pop quiz.
Very good.
Oh, we have a quiz today?
You might have a quick little checkup in class today.
It's not hard, I promise.
It's not hard, I wrote it. It's really not. It's very basic. So, all right. The last thing would be simplify. So if we had like the third root of 125 x to the 5th, y to the 6th, z squared. Okay, so we could write this as this. To what power? Cubed root is the 1/3 power. Good. So it's like 125 to the 1/3, and then x to what power? 5/3. Y to the 6/3. Z to the 2/3. So what is the cubed root of 125? 5. It comes out. All right, 3 goes into 5 how many times? Once. How many are left over? 2. 1 comes out, 2 left under. 3 goes into 6 how many times? 2. Nothing left over. All right, 3 goes into 2. No, it doesn't. 3 does not go into 2. So that whole Z has to stay under. So this, there really shouldn't be that big old gap, but this is the simplified radical form.
Wait, so when it's like x 5 divided by 3, you're just dividing it?
Yes.
Okay.
Yeah, you say how many times does this go into this? Because that can come out from under the radical. The remainder, what's left, has to stay under the radical. So if I had x to the 7/3, how many times does 3 go into 7? 2. So 2 x's can come out. How many are left over? 1. So 1 stays under. Okay? So let's do another one. Let's say we have m to the 9/4. Okay? How many times does 4 go into 9?
Wait, no, twice.
Twice. And how many's left over? 1. But because this is a 4, this is a 4th root. Okay? So let's look at this. What if we had 36 to the 1/2, x to the 3/2, y to the 8/2, z to the 5/2. What would that simplify to? 1/2 power means square root. So what's the square root of 36? 6. 2 goes into 3. 1 time. How many are left over? 1. 2 goes into 8. 4 times. 2 goes into 5. Twice. And how many are left over? 1. Does that help? Okay. And then the rest would be the word problems. Okay, so I want you guys to work on these. You may work together. Make sure you ask me questions, and then we're going to go over them. How about, for sake of time, let's do the odds. Let's do the odds. Oh, yeah, go. Just the odds. That way we have a chance to go over them tomorrow before your quiz. If we don't get a chance to go over them today. So far,